So today we're going to do addition and substitution in the first half of class. And then in the second half of class, we're going to go through two types of elimination. When you write exams or you write the diploma, you're only going to have to use the word elimination, but I go through the two types, dehydrohalogenation and dehydration, because they happen totally differently. On Monday, our next class, we'll do esterification. That's those compounds that had that O in the middle that some students have been seeing in their workbook. And right after esters, we'll go right in the lab and make them. So I'll jump right into addition chemistry. Okay. In addition chemistry, you're going to be breaking double or triple bonds. I want to talk a little bit about why they're unique and break so easily before we start doing it. Okay. When you have a double or triple bond, the first bond is fundamentally very different. The first bond is a sigma bond. Going back to Chem 20 AP, a sigma bond is just a bond right between two nuclei, or right between two atoms. So if I put a dot to represent the nuclei of two atoms. Okay. If we have some circled shape orbitals, or these are just, these circles are where we're going to find the two electrons in a bond, okay, if this is new to you. Okay. When you have two circular orbitals or electrons in circular space, and when they overlap in between, you get a sigma bond. So this is an s orbital that's a circle or a sphere, an s orbital that's a circle or a sphere. The overlap in the middle, we call it sigma. Okay. All you really need to know is the very first bond is always sigma, and that's the short message, is you don't even need Chem 20 AP to realize. The second or the third bond that we're going to be breaking in addition chemistry are from p orbitals, which look like two figure eights. And the dots I'm putting, the one there and there, that's a nuclei of an atom. So there's an atom here, there's an atom here. This is a p orbital, that's a p orbital. The overlapping not between the center of each atom, it's above and below. And that leads to a pi bond. And pi bonds are really quite weak. And at room temperature, they'll break. So we're not going to do an addition lab. We would certain years, but the chemicals require being in the fume hood. And with COVID, there's no way I can have the whole class around the same fume hood. It just doesn't make sense. There are lots of videos online, so I'll probably put a video from YouTube showing this chemistry. And yeah, you just mix the chemicals, they react at room temperature because of how easily these pi bonds can be broken. Okay. Relating all of that, maybe slightly complex terminology to what we need to connect with it is if I draw propene, now I've intentionally left a bond out. We're missing a bond here right now. All of these black bonds are sigma bonds. The very first bond between any atom is going to be right between the two atoms. And a sigma, and it's really strong. Takes a lot to break it. You need a catalyst or high energy, high temperature to break it. A second or a third bond is always a pi bond. Okay. So that second bond in the double is that weaker one, and that's going to break easier. So students sometimes are like, how do I know when to break the bond and add something in? It's if it's that second or third. Really don't need Chem 20 AP to realize it's just the second or the third. Okay? But those who've done 20 AP, you can kind of understand the orbital reasoning why.
Good morning, everybody. Hopefully everyone had a great night. Today is Friday. Yesterday.
Okay, so I drew propene. I wouldn't need a number because that double bond would have to be in the one position no matter what. We're doing addition chemistry, so we're always going to be adding a diatomic or a two-part molecule. We'll even later add something like water that's not diatomic, but two parts. We'll view it as an H and an OH and add it. Okay. When you're trying to identify or understand addition chemistry, you've got to find that double bond and realize that's what's going to break. And when that double bond breaks, we gain a bonding capacity on each side of where that double bond is. And that's why we can add a diatomic or a two-part molecule in, and it's always going to be adding something to the left and the right where that double bond went or was broken. Okay. You don't have to update your notes. I'm just going to color code this. You certainly don't have to color code answers. Okay. I'm drawing in all of these sigma bonds that never changed. There's a broken bond. This bond is going to break, and hydrogen will add in its place. So we're switching from an ene and turning it into an ane. Processes like this are really important for the oil industry. They may make a lot of product that nobody wants to buy, but maybe lots of customers want to buy the ane, so they have to run a process to turn a less valuable product into a more valuable product. Okay, what happens to come out of the ground doesn't perfectly match what consumers and businesses want. Okay, we'll go one more step. I'll add in another pi bond into this reaction. So now we're going to have a triple bond, propyne. These are slightly dangerous in drawing. I want to throw H's in the middle, but the bonding capacity is already used up. This bond, this carbon 3, and when there's 4. Now, I could be writing this as H2, and you can write it as H2. I'm breaking it up to show you the two, what goes on the left and what goes on the right is why I'm splitting it up. So now we have 2 bonds that can be easily broken, and a third sigma one that can't. So when the second bond is destroyed, or I'll call it the double, we add in 2H, and then when the second pi bond goes, we can add in another pair. So we can go from an ine down to an ane. Okay. Now you have to balance your chemical reactions when you draw them. So this is not balanced. I need 2 of these, 1 for each of the pi bonds that I broke. Common questions, your second quiz on Tuesday, when you're quizzed on this, I'll ask you to draw and balance, name the reaction type, and name all the products are the questions that you're going to get. Drawing that same triple bond again. You might have a circumstance where you have the triple bond, the alkyne, and you're told that you have 1 unit of hydrogen added. And you would get that if you put in 10 moles of this compound and 10 moles of this. There'd only be 1 of those for each of those. Okay? If you get a question where you only have 1 of those units, you only have enough to break the first pi bond. You just don't have enough. You could break the second, but you don't have enough chemicals, so it doesn't happen. In this case, just break 1 of the bonds. I'm just not color coding this one. And I got to double check my H's. 4. So it's a 1-to-1-to-1 ratio. Okay. Typically on a test or exam, for this middle case, they won't say 2 units. They'll tell you that there is excess hydrogen. There is as much as you need, and you need to figure out, do I just use 1 because it's just an ene, or is it an ine and you use 2? Okay. So be expecting to see the word excess. So that's adding hydrogen. Okay. We get a very similar process, almost identical, if we add our diatomic halogen. So I'm going to do chlorine, but iodine, bromine, and fluorine would also react exactly the same as these bottom examples. I'll just do one of these. I could have went Cl2, but I just want to really emphasize the two pieces. Okay, and just like we can add hydrogen, we can break that pi bond and go from an ene to an organic halide. So enes are nice building products. You can add lots of different two-piece molecules and go from the ene family to the ane family to the organic halide family, and we're going to see to the alcohol family shortly. And we're going to get a 1,2-dichloropropane, because I would have to name it from this side. Okay. And that is balanced. We just need one of all the materials. Likely I may ask you to, I'll say, draw the structural formulas of all the products, but I only ever mean the organic compounds. Okay. So if you make water or there's chlorine, anything inorganic, you don't have to draw those out if you don't want to, but all the organics will ask you to. Okay. We're going to make it not really much more difficult, but we're going to add in, what if it's not the same? What if it's an H and a Cl? Okay. What's going to happen there in terms of products? How many, the reactions? So HCl. I'm going to draw propene again. And I'm just going to color code the addition so it pops out. There's our pi bond, our second bond, so that's what's going to break. And then I will add in my H, and I will add in my Cl. Now that works and that can happen, but it's actually not our only option now. We've got to think a little bit more and write all the possibilities. Before, it didn't matter how the H plus or the H2 added. But now, this HCl, I added it this way, but I could have flipped it around and added it that way. You have to write all possible products. So this is one of the possibilities. Okay. Plus, we've got another product. The Cl could have added in the middle and the H on the outside. Both of these are possible. They're not actually 50-50. You'll learn in your first university organic course which is the major and which is the minor, but here you just write all the possibilities. They won't be equally likely. So I've predicted all the products. I've done that part. I'm not going to name these because they're simple names, so I'm just not going to take the time to do that part. I do have to balance them, or they're not correct reactions. So I made two prop stem compounds. So there's 6 carbons here. I need to make sure I have 6 carbons at the very beginning. So I'm going to need 2 of those original reactants, and I'm going to need 2 of these. Now I'm balanced. You'll find in organic chemistry, you don't actually have to count up all the atoms. Just know if you make 2 hydrocarbons or hydrocarbon derivatives, you're going to need 2 original materials. If you use 2 small molecules, you're going to put a 2 in front. Okay? You could go and count all the Cl's, but you never have to do that here. Just sort of balance them by groupings. So that's making an organic halide. We're going to make some alcohol now. Propene again. Almost every example today is propene. I only have a couple that don't start with that. And now I'm going to add water. I jokingly call this kind of Santa water the way I draw it. HOH, kind of like ho ho ho. Okay, but I'm drawing it this way because this is how it's going to break and add to the organic molecule. So that's my reasoning. Okay. On a test quiz, you might just see H2O, and you have to realize that's how it's going to break apart and add to our organic compound. Now, that also, the right and the left are different. We got an H and an OH. We're going to have that same two options to add, just like we saw previously. So I'm going to kind of lay the two of those out right away. First option, I'll add it in the same sequence that I wrote it at the beginning, H and then OH. So propane 1-ol, or the OH could have added there, propane 2-ol. Okay. Make sure when you go to draw it both ways that they have two different names. It will come up that if you add it this way and that way, occasionally, it'll still be the same structure. It'll have the same name. You would not draw both of them if they had the same name. So if I added this to just 2-carbon to ethane, so I'll draw that next and show you that. Okay, so it could add both ways, but make sure you get two different names. I made 2 products, so I'm going to need 2 of those and 2 of those. Now I'm balanced. I've done everything except for naming the products. You would get quite a mess, and you will not get that in this course. So your thinking is right, but we're going to stick to 1 double bond in terms of assessing you. But you would quickly get this exponentially growing number of products, but depending on the number of pi bonds, and it would just suck. It would turn into a mathematics problem is what it would turn into, figuring out all the combinations. So I'm drawing a different starting molecule for the first time. This is ethene. And I'll add water to it. The pi bond will break. HOH. We get ethanol. I don't need a number because this can only be in the one position. And I could not draw another example where the OH is on this side because it would still be ethanol. And if you draw both, you're incorrect. You might think you're being better, but you're being worse. You're drawing the same thing. So one of those and one of those just makes one product. And that's addition chemistry. Take your double bond, add whatever you're given across it, think whether it matters whether when you flip it around, does it give you 2 products or 1. So addition chemistry, you either do 1 product or 2. That's the only 2 possibilities for answers. Okay. We're going to go into substitution, and this is a bit more of they're a lot messier. There's a lot more products. I'm just going to do 1 example because it's going to take me much longer to go through. Okay. And then it happens slightly different with an aromatic compound. So we'll do an example with substitution with an aromatic, and then you'll be practicing these 2 reaction types. So realize we took a jump. We've left addition. We're now going to switch. So I'm not adding students to my class anymore. I'm doing a trade. I'm not going to say any names, but one person is going out, and I'm going to get somebody new. That's what's going to happen here. hydrogen atoms, okay, can be replaced, okay, we're going to say substituted, okay, in an alkane. Okay. So we have a very different family now. So when you get a test and you see an alkane, you're thinking substitution. You get an alkene, you get an alkyne, you're thinking addition. But we're breaking those very strong sigma bonds now to get those H's to come off. So you need a catalyst. Okay. And the most common one is ultraviolet radiation or UV light. If you actually just set this out in the sun or even right next to a window, this reaction will occur with the energy from the sun. You would not want to start this at the very bottom of a page because you're going to take up maybe half a page of your notes filling in the many products that I have to draw. So we're now going to be doing a switch. One of these BRs are going to switch out one of those H's when we have that ultraviolet radiation that can break that really strong sigma bond and get it off for us. I'm going to start by substituting that H away. That H goes away and a BR takes its place. I'm going to get a 1-bromo product. H went away. That's where the H was located. I'm going to put a BR in its place. Now, the UV light is a catalyst, and catalysts are written above or sometimes below arrows. Okay, so I'll add that in. Okay. So that's our first substitution. This isn't balanced yet. Can anybody help me balance this first step? Now we're good? No, we're not good right now. Like a little two here. Well, we started with 2 BRs, and there's 1, and there's 2. So that part is okay. Yeah, you get hydrogen bromide. So he said bromine. I didn't pick on him, but bromide would have been a better word. It's the ionic form. So we've got this H that I circled in yellow came off. That H is this H, and then there's an extra bromide. Okay, a BR gets added here, and 1 gets left over with an extra electron, and this is an ionic compound. So that's no balance at first step. Okay. Now let's figure out how many different H's could pop off and give me this, because I don't want to draw all of those. Okay. Like this H could have come off and would get the same product. I don't have to worry about that one. It's the same thing. Okay. What other H's could come off and I would still get 1-bromo propane? At the end, there's 2 ends. You're going to have to a little bit more. On the right, so like this guy. Yeah. So that, if this H gets substituted, we get that 1-bromo, or this H, or this H, or there's that last one where I started, that's at the end. Any of those H's would give me that product. Okay, so I don't need to worry about any of those in terms of other possible products. So I'm going to kind of move along and focus on that H and see what would happen if that H got substituted. So I'm going to draw in all the H's except for the second one from the left. So I've substituted a bromine in its place. Okay. Now this bromide can't substitute in. Only bromine can do the substitution. Okay. If you actually look at the mechanism, the ultraviolet light is going to break this guy up, make a radical. So the first step involves the diatomic bromine. So we need another one of those. One of the BRs adds in, the other BR pairs up with the H that comes off. And that's our second organic product, or fourth product if you're counting all of them. So that's a 2-bromopentane. That H would give me a 2-bromopropane, pentane, sorry. But so would this H, and so would that H. So I've covered in those two products all the yellow H's, all the orange H's. I've got 2 left in the middle, and they're both the same. Okay. This one or that one is going to give us our third and last product. They're both not going to come off. The top one could have come off one molecule, the bottom one could have come off a different. If you put, you know, even 1 mole of propane into a vessel, you have like 10 to the 23 individual molecules of it, billions and billions and billions of them. So some of them will do one type of reaction, some will do another. So we are almost done. There's our 3-bromo, an H comes off, and it pairs up with the second BR, which is a bromide. And now we have all of our products, 1-bromo, 2-bromo, 3-bromo. If you're doing this on a quiz, you could just go 3 HBr, and that's fine. Either way, you could write them out individually or lump them all together. You're balanced either way. But everything isn't balanced yet. Okay. Hopefully you see that the start I never balanced. Okay. So I've got and I typically don't do that to the very end. So we made 3 organic products, so I need 3 of those original starting materials, and I'm going to need 3 of these, 1 to do the first, 1 to do the second, 1 to do the third. If you count, you'll end up 3 pairs, 6 bromine atoms, and there's 6 BRs on the product side. Yes, what is possible, but we're not going to do, is that once you've made this product, a second reaction could occur. If you've got more bromine and more ultraviolet light, this guy could then react again. We're not going to do that. So yes, it does happen, it's possible, but you're just going to show the first product, not subsequent steps. So good question. Yes, it's possible. No, it's not on your assessments. Okay. So this is what 95% of your substitutions are going to look like. Okay? You might see a aromatic compound involved in substitution. You might see a benzene ring, particularly to test your knowledge of chemistry. And I'm going to draw it maybe what I'll call the most incorrect way to do it. It's still correct, but it has all these double bonds. Students mess up addition and substitution all the time. Students quite frequently, particularly when they're first starting and haven't practiced as much, see an organic compound, see bromine, and give me a 1,2-dibromo. They want to add both in. They want to do addition and not substitute. They're even more likely to make that mistake with benzene, particularly if I draw it like this, because they think, oh, they see 3 double bonds and they want to do an addition to a double bond. But there are no double bonds there. That's just how we draw it. But we really have delocalized electrons. So when it reacts with chlorine, we don't get 2 of them adding. Okay? We'll see a substitution reaction. Okay? You still need ultraviolet radiation to drive this substitution reaction. Okay? And you actually need another catalyst. You need iron 2 chloride. Okay? To get this substitution to occur. Okay? And you'll just do a substitution. Any one of these H's can come off. It doesn't matter which one, because it's going to be the one position on a ring, whether it's this H or this one. You're going to have 1 chlorine. It'd be a 1 chloro, and you drop the 1. And just like before, we've got the H coming off, and we've got an extra Cl left over. So we're getting hydrogen chloride out of this reaction. If this was aqueous, which it probably wouldn't be because that's not polar, you get hydrochloric acid. But if it's not aqueous, you get hydrogen chloride, which is a gas. I'm going to leave it at that example. Just realize it gets a bit more complicated if you did start. Maybe that's your starting material and you do a substitution. If I go to add, let's say, a Br to this in substitution, I add molecular bromine, then the bromine could go there, there, or there. And then you can get multiple products if there's something already on the ring. But if there's nothing on the ring, you only get 1 product. Okay? Now, we could add a Br there, there, or there. I wouldn't keep going there because this would be the same as just adding it there. Okay? And that is substitution reactions. So we're slowly going to build. I'm just going to get one more thing out, then I'll get your question. By the end of today, we're able to sort of mostly do this flow chart. But for students in Chem 20, you can almost make this cookie cutter by look at family and what families do. Because we're only going to see families do 1 type of reaction, except for alcohols are going to be the only thing that have 2 options that you have to worry about. But most things, it's just 1. Okay. If you have an ane, what type of chemistry did they do reaction-wise today? They did the substitution. So that's what we just did. Okay. Now you do need ultraviolet radiation, but that's the only thing you're going to see anes do in this course. Okay. What we started with was our ene or our ine, no catalyst needed, and they can do addition. So this is how you really want to tackle this unit. Identify the family, know the catalyst, and you can really figure out what's going on fairly quickly, hopefully. I'll just get Aaron's question and then you are.